minus 10, 9, 8. We have a go for main engine start. We have main engine start. 4, 3, 2, 1, 0, and liftoff. Liftoff of the space shuttle, and it has cleared the tower.
Looks like slow. It is slow. That's the case.
Yeah, your touchdown.
Hello and welcome aboard the Space Shuttle Endeavour, where we're orbiting almost 300 kilometers above the Earth. Our primary mission on this flight was to deploy a Tracking and Data Relay Satellite, or TDRS for short. And when it becomes operational, it will relay communications between orbiting spacecraft and tracking stations on the ground. A few days ago, we sent the satellite on its way.
Houston, Endeavour.
Go ahead, Endeavour.
We have deployed the IUS TDRS.
But deploying TDRS wasn't our only mission on this flight. Two of our crew members put on the protective EVA suits and went outside the orbiter on an important spacewalk.
We also have several science experiments to conduct, but for one of our experiments, we brought along some toys. Each of these toys work because of important scientific and mathematical principles, principles that we often take for granted on the ground.
But things can work differently in space than they do on Earth, even toys. That's why when we're orbiting the Earth, we experience something called microgravity. That means that everything around us, our space shuttle, astronauts, even toys, float as if they have no weight.
If you don't understand microgravity, your teacher can help you out. But for now, we need you to help us with these experiments. We want to find out if the toys act differently in space than they do on Earth. But first, we have to know how they work on Earth. This is where we need your help.
We want you to experiment with the same kinds of toys we have here on the shuttle. Then, when you become experts with them, try to predict how they will act in microgravity. After you've made your predictions, watch what we do with the toys and see if you are right.
Remember, this is a team effort, and we're counting on you to make our experiment a success.
In this scene here, I'm trying to get the rat to flip on my hand, but as you can see, what happens instead is that his legs push against my hand and he spins up and away. Now in the next scene, what I did was tape his feet to a book. Now the book is so much more massive than the rat that when the rat pushes on it with his feet, the book turns only very slowly, and the rat, because he's taped, cannot jump up and away like he did with my hand.
Watch what happens when the suction cup releases now. You can see the spring jumper takes off. We'll watch it again. And boy, look how fast that travels across the spaceship. It really surprised me. We'll watch it slow motion here, and you can see it tumbling coming off the lockers.
The big question with this scene is, will the frog swim as well in air as he does in water? Well, if you watch the picture here, you'll notice that no, he does not. I try all different ways of getting that frog to swim in a straight line, but because the air is much less dense than water, I can't get him to do it. So the frog just flops around.
Take a look at the submarine here, and I'll let it go, and you can see that as it turns through the air, both the propeller and the submarine turn, instead of in the water where only the propeller turns. Now I'll take a look at what happens if I hold on to the propeller, and you can see that the submarine turns around it. Then I'll let both go, and it takes off. One more time. This time I've attached small pieces of paper onto the propeller to make the propeller larger. And we'll see what happens when we let this go. I'll move back so we can get a greater view of the line of travel. Let it go and it really takes off.
We've taped a pen onto the end of the submarine propeller to see what would happen and if the submarine would change the way it moved. Well, it turns out that it did. As you can tell, it flops around quite a bit more, and we had a harder time keeping it under control.
Let's look at the swimming fish. Now this fish swims real well in water, but watch what's happening now. He's really struggling and not getting anywhere. Just sort of floating around. Really doesn't swim very well in air. We'll try it one more time. Whoops, I think I had a little rotation, and he's turning around, just sort of flopping around, not really getting anywhere, trying to swim through air.
One of the things you can do to help the fish swim better in air is to increase the size of the fin. It also turns out that releasing the fish very gently has an impact on which direction the fish will swim. I finally got it right in this scene here, and you see the fish swimming forward.
We'll look at the flapping bird in microgravity, and you can see what happens here. It just flies around in circles, doesn't seem to have any direction of travel. Let's look at it again in slow motion. Just goes around, doesn't go straight as it does on the Earth in one gravity. And it looks like it's turning around the wings. Now we'll just soar it without the wings flapping. And it soars across the middeck. I tried throwing this paper maple seed several different ways. You can see it didn't go very well when I threw it holding onto the wing. Now I held on to the bottom and threw it, and it turned just a little bit. I finally got the hang of it, and you can see it turning now very much the same as it does on Earth. I'm throwing the paper boomerang, and we'll see what happens. It goes into the side of the wall. If there had been more room, I think the paper boomerang would have come back. Now this time I threw it and flipped it with a lot of rotation, but not much forward velocity, and it just keeps going straight.
Boy, that thing shot up like a rocket, and that caught me by surprise. I didn't expect that in this microgravity environment that it would go up that quickly. Even in slow motion, it comes off and hits me in the chest even before I can react. Here I have a single graviton that's floating free in the cabin, and it's spinning. You can see it wants to spin about the wheel inside as well, so you see the outer case spinning also. But I'm trying to get it to tip over, and I can bump it on the sides, on the top, on the bottom, and I can't make it tip over. It's stable about the axis I let it go in, which is the spin axis is up and down. This is the same configuration. I've got one spinning graviton here, and I've oriented it so the spin axis is pointing at the camera. Again, I'm just bumping it on the sides and the top and the bottom, and I cannot get it to tip. It's stable about the axis I let it go in. This should be a graphic demonstration of a spinning and a non-spinning graviton. You see the spinning graviton stays stable while the other one tends to tumble end over end because it has no stable spin axis. I'll do this one more time. You can see that one is spinning and one is not, and the one that's not spinning just tumbles free while the other one maintains the orientation I let it go in. Okay, here I have two spinning gravitons, and they're both stable as they spin here. And I take one and bounce it off the other. You can see this time, because they're both stable, they don't tumble. Neither one of them tumbles, as you might expect. Now here I have a curious combination of two gravitons that are attached together on a wiffle ball. And I have them both spinning in the same direction, so I would have thought they'd be very stable in this configuration. But because they weren't perfectly aligned with each other, they got out of hand. Wham! Came apart and really gave me a surprise. Let's take a look at that in slow motion. You can see how the misalignment causes them to break apart. Now this time I took those two gravitons and I rotated them in opposite directions from each other. And because their angular momentum vectors are in opposite directions, their stability axes cancel each other. So I'd expect to be able to let this go and just have it tumble. Now obviously I can't make them both spin exactly the same speed. So the one of them is going to have a little bit of stability, but you can see I can bump this stack and I can make it wobble around a little bit. As I bump it here, you see it will wobble some. It has some tendency for stability, but not as much as a single graviton would have floating on its own. And I can make it wobble pretty wide end over end. So having two of them spinning opposite directions canceled each other. Now we're getting complicated. I have three gravitons all hooked to the same wiffle ball, orthogonal to each other. That is, their alignment is 90 degrees to each other. And I'm going to spin them all in the same direction with reference to their attachment to the wiffle ball. Now, as I do this, you would expect that the angular momentum vectors of each of the gravitons would add up to a single vector which would be right between all three. So as I let this go and it tends to rotate, the only axis that it will rotate around is an axis that you can see if you put a pencil between all three of the gravitons. It's rotating about that axis that's equidistant from all three of them. Now as it continues to spin up by the natural character of the friction in the gravitons, it eventually spins up so fast it comes apart. Well, here's the same combination again. I have three gravitons mounted orthogonally to the wiffle ball, and I'm going to spin them all up in the same direction. And before I spin them up, you can see how they tumble end over end. There is no stability there because none of them are rotating. Now, as I spin all three of them up, initially when I let them go, you'll see them begin to rotate around that same axis that's right between all three. But one of the gravitons comes off, and look what happens to the remaining two. As that bottom graviton came off, the remaining two gravitons now are rotating around an axis right between the two of them. And again, I was lucky I didn't get beamed by this graviton as it came off toward me. Now here's an experiment that's a good demonstration of how a non-spinning graviton behaves just like a ball on the end of a string. I can change the axis of rotation just like you could with anything attached to a string here on Earth. But once I spin this graviton up, look how it maintains that stability around its rotation axis. I can spin it around and around, and it wants to stay in an orientation so that the spin axis is parallel to the axis of rotation that I'm holding the string in. Now look how I changed the orientation, and eventually the graviton ended up changing the orientation of its rotation so it matched the rotation axis of the string. Very interesting change in the way the graviton behaved. Eventually I'll take it back to a horizontal rotation, so the rotation axis of the string is vertical, and you'll see the graviton again orient itself so its spin axis is vertical to match the rotation I'm making with the string. This rattleback is a very curious device here on the ground, because if you rotate it on a table, it will eventually turn around and spin the opposite direction. Now what you're seeing here are three sequences of me spinning it around each of its axes. I spin it end over end with the thick side horizontal, and then end over end with the thick side vertical. And then in the last sequence, I spin it around its longest axis, and you can just see it spins. In no case did it ever turn around and do the peculiar things it does on a table.
I was playing with the clacker balls one afternoon on the shuttle, and I had let them go and they drifted apart and they did this funny motion. So what I tried to do was get that funny motion to repeat itself. I experimented a little bit. I tried various different actions by spinning them in one direction or the other. I wound up taping the clackers so they stood apart, and then I flipped them first end over end, and that didn't seem to repeat the motion that I accidentally had discovered. And then spinning it around along the axis of the handle produced the flipping motion that you see here, and that was quite remarkable. As it spun around, there was a little bit of imbalance, and it seemed to flip end over end, which was unexpected when I first took them into space. Before flight, I had to practice with the clacker balls a bit since I had never played with them before. I became quite proficient at using the clacker balls in this fashion. However, while I was able to get one ball to displace the other on the ground, I was never able to get the clacker balls to do this in space. It was more difficult to produce this motion with the balls in this orientation relative to my body. In this next orientation, it was a little bit easier to get them to even come close to displacing one another, but I was never really successful. I believe it was easier here because of the orientation of my arm relative to my body, made it just a bit easier in getting the balls to behave as I wanted them to. On Earth, gravity produced just enough drag on the stationary ball by weighing it down just enough so that you could produce the desired motion. That is, have one sit still and the other one spin around and hit it, and then it staying still and the other one continuing the motion.
This experiment is a demonstration of the concept of momentum. The racquetball has less mass than the pool ball, and as a result, after a collision, it will always travel faster than the pool ball, even if I throw the pool ball at the racquetball. Here you'll notice it does move faster because it does have less mass. Now if I tape the two of them together and again hit the racquetball with another pool ball, you'll see it curves around the pool ball. In this final demonstration, I hit the two pool balls, and because the racquetball has not been hit, it just goes along for the ride.
This ball and cup was one of the more difficult toys I've demonstrated on the flight. You can see that the ball just won't stay in the cup as it does on Earth. Of course, on Earth we have gravity holding the ball in the cup, but in this microgravity environment, when I put the ball in the cup and then push to hold it, I've actually pushed the ball away. So I never could get the ball to stay inside the cup. We'll try again. You can see I just push on the ball and that pushes the ball out.
In this scene, I try to throw this ping pong ball the old-fashioned way, but it doesn't curve down toward the target like I would expect on Earth. So I have to change my throwing style. I throw it straight at the target without any twist at all, and then I attempt to throw another ball with some twist to see if it changes the direction of the ball as it goes to the target. Let me try this again. Straight with no spin, Oops. Now one thing you'll have to remember is that the Velcro of the ball does have to touch the target. Let me try this again. There we go. And then I'll throw it one more time with some spin to see if the trajectory toward the target curves. Looks to me like it did a little bit. Now in this scene, I take the target off of the lockers so that it's free floating, and this is a good demonstration of how one object will react when you hit it with another object in space. Now it's floating around in part because of the way that the first ball hit it, so I'll throw another ball to try to change the direction of the floating. I got it to work. Horseshoes isn't played the same way in space as it is on Earth. Here I try to throw a shoe the old-fashioned way, and as you can see that without the effect of gravity, the shoe just bounces off. I try it one more time, just to demonstrate the point, and then I decide I'm going to change my technique. Instead of throwing the shoe right at the pole, I'm going to use a spinning motion to see if I can catch the pole. And in fact, that's exactly what happens. At this point, the shoe is pretty stable in a spinning motion around the pole, and in fact, this ended up spinning for a total of about 5 minutes. Without the effect of gravity, it doesn't slow down and settle at the bottom of the pole. In this demonstration, I take the horseshoe pole off of the locker and let it free float while I throw the shoes at it. That didn't work too well. In this demonstration, I decide I'm going to throw a horseshoe at the pole in 3 different places to see how the pole reacts. In the first demonstration, I throw it as low as I can to the base. And as you can see, there isn't much spinning motion of the pole itself as it reacts from having the shoe thrown against it. I'm going to try a different technique. How about the middle? Okay, I begin to see the pole turn as it reacts to the shoe being thrown at it, and it floats away. One last try by throwing this horseshoe at the tip of the pole to see if I can get it to turn even more as it free floats away from me. Certainly seems to.
Basketball is a sport that's near and dear to my heart here on Earth, and I was very interested in seeing how basketball would be different in space. As you can see, I start out with a standard free throw type shot, and the ball just caroms off in a funny direction, not anywhere close to what you would expect from shooting the same shot here on Earth. So I keep changing the angle from which I'm shooting, and I'm finding that it is pretty darn tough to make a shot in space. Finally, I look at it, and I think that the only way to get the ball in the hoop is either to come up real close and slam it through, or to try to bounce it off the ceiling. That's the only angle that seems to work. And note that the ball stops in the basket. It doesn't get pulled all the way through. The next thing we tried was attaching the hoop to a free-floating book. You can see that every time I hit the book, which is now the backboard, with the very lightweight basketball, I can actually make the book and the hoop start spinning. Well, that makes life difficult when you're trying to make a basket up there, and I ended up coming up with a very simple approach. Just hold the book steady. Otherwise, it becomes very difficult to make a shot with a free-floating basket and backboard. One of the things that's always impressed me here on Earth was the ability of the professional basketball players to spin around and make these really neat moves. Well, I was trying some of that in space. You can see it's pretty difficult. It's hard to control your body up there. I finally managed, after a while, after a number of tries, to figure out a way to go head over heels and accomplish a slam dunk. This is my entry into the NBA Slam Dunk Contest for next year.
Now I know on Earth you think this toy works very well, but in space we couldn't get it to work at all. We had this thing floating around, but without the effect of gravity, it just doesn't work the same way. Now I took this toy, looked at it for a number of minutes, and tried to figure out what in the world do I do with this thing up here. It took me a while to finally come up with something that appeared to be unique in space about this toy. Watch when I close and open up the Jacob's ladder. Every time I did this, the ladder would turn into a different configuration. It was completely random, and we, the astronauts, couldn't ever really predict what would happen when we pulled apart Jacob's ladder. To this day, it still seems a mystery.
Here I am trying to produce standing compressional waves by holding one end still and moving the other end in and out. The result had some transverse motion to it because my hand also had some up and down motion. In the next sequence, I tried to produce compressional waves by moving my hand in and out a bit faster. Then I tried to produce the same type of wave by moving both ends. Next, I tried to stretch the wave out. And then I transitioned to producing transverse waves, first slowly, and then with a higher frequency and amplitude.
These magnetic rings are really interesting. I've got them arranged on this plastic rod so that the poles of the magnets are opposite to each other and they repel or push away. And you can see when I release the rings, they spring out equally along the plastic rod. And it doesn't matter whether I hold the rod up or whether I hold it down, because in this microgravity environment there is no up and down. They spread out equally along the plastic rod and push away from each other. Now I'm going to rotate the plastic rod very slowly. We'll see what happens. The rod is rotating so slowly that the magnetic force still keeps the rings pushed away from each other, and the spacing is about equal, about what it was before. Now I'll rotate the rod faster. Now see what happens. Now the rotational force has overcome the magnetic force and the rings are pushed together.
The magnetic marbles were a lot of fun to play with. What we were looking at initially was how far apart can we hold two marbles and have them still be attracted to each other. The first time we did it, we had the opposite poles facing each other so they would be most attracting. The second time we tried about the same distance apart, only with the like pole facing each other, and sure enough they attracted there as well. This time the marbles were just a little bit too far apart and they didn't attract. I put them closer together, but I started the one on the right in your screen with a little bit of motion. And that motion was just enough to overcome the attractive force, so they did not come together. Now I'm looking at the influence of one marble on the other without touching it, seeing how close I can come with one marble and how much I can make the second marble, which is free-floating, spin as a result. You can see that every time I make a pass around the marble, I'm affecting the spin of the marble, and actually I'm even pulling it towards the marble in my hand. Now I'm looking at releasing one marble with two marbles attached together to see if there's any difference in the attraction. It looks like the two marbles are pretty happy being by themselves and that third marble is left out. This time I'm putting the third marble in motion, and sure enough, if it gets close enough, it is attracted by the other two. Now I have strings of 4 marbles each, and we're going to see if they come together. That's a funny looking snake-like thing. We got a big kick out of seeing that. And then you tap it in the middle and it turns into a ring. This time I have 2 sets of 4 marbles, and they had the like pole facing each other, so they were repelling each other. And they would swing back and forth, and they actually did repel each other. And they're pushing each other away. Now I've got 1 set of 5 marbles, 1 big one in the middle and 2 little ones on either side, and I'm seeing what influence I can have on those 5 with 1 small marble. And look, it attaches to the end of the string. This time I start with the blue face of the small marble and the 5 marbles together facing each other. Initially they repelled, but eventually the attractive force overcame it and they came together. The next thing we took a look at was a string of marbles. We wanted to see how they reacted when we spun them around. As I spin them, it becomes more and more difficult as I go faster and faster for the marbles to stay together. Where do you think they're going to let go? Now I have 2 rings of magnetic marbles. I pass them very close to each other and they show no sign of attracting. They seem to be very happy just being on their own little ring. But if they get close enough and they're moving slowly enough, they will attract. Now let's try it with them very close together, moving very slowly. You can see they just are very happy to be on their own, and there is not nearly as much attractive force as there was earlier with the 2 individual marbles.
The comeback can wasn't quite as interesting on orbit as it is here on the ground. I could let it go here as I spun it up, and you can see how its rotation rate increases and decreases as the metal weight catches up. I also tried to spin it up before I let it go, and you can see it rotates quickly one direction, then slightly goes the other direction, back and forth until it comes to a stop. But because you can't lay it on a table and spin it up and have it roll down the table or come back to you as you let it go, it's not as interesting here.
In this first sequence with the car and track, I had wound the car up and just let it go without the track. And here, because of action-reaction, you see the car doing an end-over-end wheelie. Next, I tried to get the car to run on the wall. The main result when I release it is that the car springs back toward me off the wall from the little force I had applied with my hand to hold it there. Getting the car to run on the track was a bit easier in space than on Earth because the car didn't have to build up as much velocity to stay on the track as it did on Earth. In the second sequence, I got the car started and then let it go. Here you see that second sequence in slow motion. Wherever the car is on the track, the whole system, car and track together, moves toward that general direction. Next, I started the car on the track by giving it a push rather than winding it up. In this case, we wanted to see how long the car would stay on the track if I held the track steady enough where I wouldn't bounce the car off the track. Even though I knew intuitively, by the laws of physics, that this would be the case, it was amazing to me that any forward velocity of the car at all was enough to provide the necessary centripetal acceleration to keep the car on the track. Here in this second sequence, where I just push the car rather than winding it up, in this view, the car ends up stopping on the top of the track. This was amazing, even in space, to see the car creep along ever so slowly and then stop and sit there at the top. Finally, the car comes off the track and winds up in the center of the track before they both slowly drift away. Next, in a demonstration of centripetal acceleration, I get the car started on the track and then open the track. Once there is an opening, the car flies out in a straight line.
Okay, I'd just like to remind all the folks that are watching out there that, especially the children, that science applies to everything, even toys. And we hope that our demonstrations today have given you just a taste of scientific research in space. And we want to encourage all the children out there to do well in science and math, and to learn all you can about the world around you, because we need people like you to design and maybe even fly the experiments of the future. So as we say goodbye, we're going to release all of our toys at once. 1, 2, 3, now. Okay, bye-bye everybody.